Good morning friends, welcome to Engineering Mathematics 4. I hope in the last session we have discussed about fourth order Arangekutta method and Millines method, and I think we have solved a second order differential equation using both of the methods. Both the methods means fourth order Arangekutta method as well as Millines method. Friends, in this session I am going to discuss about special functions. So you may ask, what do you mean by a special functions? It is not an unknown thing. We are already familiar with differential equations. So it means we have studied solution of linear differential equation with constant coefficients. And say for example, if the given equation is second order linear differential equation with constant coefficients, or they may give higher order differential equations. Say for example, if they give second order differential equation with constant coefficients, how do we find out the solution? So we know that first we will write down the auxiliary equation, then we will find out the roots. Depending upon the roots, we will write down the solution when right hand side member is equal to 0. Sometimes right hand side member may not be equal to 0. So in that case, the complete solution of linear differential equation with constant coefficients is complementary function plus particular integral. How do you find out the complementary function? As I have mentioned, so you will get the auxiliary equation, right? If the given equation is an second order differential equation, you will get two roots. Roots may be real and equal, roots may be real and unequal. Sometimes we may obtain a complex roots. Is it clear? So in all these cases, we are able to write down the complementary function. And suppose if the right hand side member is not equal to 0, so in that case we want to find out a particular integral. So right hand side member is not equal to 0 means what? Sometimes it may be an exponential function, e to the power ax, or sometimes it may be an sin ax, or it may be an cos ax, right? So in all these cases we are already familiar with how do you find out particular integral, right? So then we are able to write down the complete solution. Y is equal to complementary function plus particular integral. So in case of e to the power ax, we are going to replace d by a. In case of sin ax or cos ax, we are going to replace d square by minus times of a square, right? So we are already familiar with all these things, and I think we have studied Legendre differential equation also. So now I want to extend the same thing. Here also they may give a differential equation, and we must be able to identify whether the given equation is a differential equation or not. But here the coefficients may not be constants, coefficients may be variables, and coefficients may be polynomials. In all these cases, how do we find out the solution of the given differential equation, right? So however, a linear differential equation with variable coefficients which arise from physical problems do not permit such solutions. Such solution means, just now I have explained. So linear differential equation with constant coefficients, right hand side may be e to the power ax, sin ax, cos ax, may not enough to solve a physical problem, right? So for that reason, in many cases it is easier to find a solution in the form of an infinite convergent series. So it means instead of writing the solution of the given differential equation in the form of complementary function plus particular integral, now we want to find out solution in the form of a series, right? So that's why we call it as a series solution. So they will give a differential equation and variables are coefficients are variables, then we want to find out a series solution, right? So how do you find out the series solution? Okay, the series solution of certain differential equation give rise to special functions such as Bessel's function or a Legendre polynomial, Hermite polynomial, Cherenkov polynomial. These special functions have many applications in engineering. Okay, now I want to find out the series solution. The series solution means using, or I want to find out the solution of Bessel's equation, right, to solve the equation of the form. So, the given equation may be in this form. So, P naught x d square y upon dx square plus P1 x dy by dx plus P2 x into y is equal to 0. Here, what are the values of, or what is the value of P naught x, P1 x, P2 x, right. So, may be a polynomial, is clear, where P naught x, P1 x, P2 x are polynomials in x in terms of infinite convergent series, right. So, clearly it is an second order differential equation, because highest derivative in the given equation is d square y upon dx square. Now, we want to find out a series solution, right. So, now I want to verify whether I am able to find out the series solution for the given equation or not, because for each and every equation we may not be able to obtain series solution. So, that is why I want to check the validity of a series solution. If it is possible, then only I am able to find out the series solution, otherwise no. Then you may ask, how do we check whether the given differential equation is able to find out series solution or not, right. So, it does not have a series solution. As such, we find the conditions under which the above equation admits of the series solution. We will come to know the condition, right. So, here I am going to divide equation 1 by P naught x throughout divided by P naught x, and this equation can be written down. P naught x divided by P naught means the coefficient of d square y upon dx square becomes 1, what I have written here, plus P1 x divided by P naught x can be written as, I will write some function, say P of x into dy by dx. So, P2 x divided by P naught x can be written as some function, say Q of x into y is equal to 0, what I have written here, right. So, P of x is equal to P1 by P naught, Q of x is equal to P2 by P naught. So, it means given equation can be written down in this form. Okay. So, when x is equal to 0 is called an ordinary point. I will replace x by 0. Where I will replace? In the polynomial. What is the polynomial? P naught x. And I want to verify, when I replace x is equal to 0 in this polynomial, whether is it equal to 0 or not equal to 0. Suppose if it is not equal to 0, in that case I will call it as an ordinary point. It means x is equal to 0 is called an ordinary point. Suppose it may be equal to 0. So, in that case we call it as an x is equal to 0 is called singular point. So, it means before obtaining the solution of the given differential equation, first I have to verify whether x is equal to 0 is an ordinary point or x is equal to 0 is an singular point. Okay. Now, you assume that I have verified x is equal to 0 is an ordinary point of the given differential equation. Its every solution can be expressed as a series of the form. Okay. How I am going to write down, or I will assume the solution of the given equation may be in this form. So, first term is a naught plus a1 into x plus a2 into x to the power 2. What is the next term? A3 into x to the power 3, next term a4 into x to the power 4, and so on. What is the nth term? an x to the power n. Like that I can assume the solution of the given differential equation, or the same thing can be written down using the summation ak into x to the power k. K varies from 0 to infinity. Suppose in this series if I replace k by 0, right. So, what I will get? A suffix 0 x to the power 0. X to the power 0 means 1, a suffix 0 means I hope we will get first term, right. So, now I will replace k by 1, a suffix 1 x to the power 1, it means I can obtain second term. So, like that when you replace k by 0, 1, 2, 3, you will get the same series. Okay. Now, I have assumed, or I can assume, when x is equal to 0 is an ordinary point, solution of the given differential equation is in this form. As I have mentioned, sometimes we call x is equal to 0 is a singular point, right, of the given equation. It is understood that the polynomial is equal to 0, and if x into p of x or x square into q of x possesses derivatives of all orders in the neighborhood of x is equal to 0, then x is equal to 0 is called regular singular point of 1, right. Okay, I have verified x is equal to 0 is a singular point. Along with that, I have to verify, can I able to find out the derivative of x into p of x, x square into q of x. So, it means first derivative, second derivative, third derivative, and so on. So, if it is possible to find out derivatives of all orders, in that case you may call x is equal to 0 is a regular singular point of the given equation, right. So, when x is equal to 0 is a regular singular point of the given equation, then at least one of its solution can be expressed as y is equal to x to the power m a naught plus a1 x plus a2 x square plus a3 x to the power 3 and so on, or by using the summation you can write down ak x to the power m plus k. Here also you can replace k by 0. So, what you will get a suffix naught x to the power m plus 0, right. So, you will get the first term. When you replace k by 1, a1 x to the power m plus 1, you will get second term, third term and so on, right. So, it means when x is equal to 0 is a regular singular point, then I must assume the solution of the given differential equation in this form, right. So, where m may be a positive or negative integer or a fraction, you can observe the solution of the given differential equation may contain m, right. So, here what is m? M may be a positive integer, m may be a negative integer, m may be a fraction, right. So, now I want to discuss all those cases. I can consider m is equal to a positive integer. So, what is the solution? And m may be a negative integer or m may be a fraction. I will take m is equal to 1 by 2. Then what is the solution, right. So, we want to discuss all these cases. And one more thing is, when x is equal to 0 is an irregular singular of equation 1. It means, so far we have discussed 2-3 cases, right. X is not equal to 0 does not belongs to those cases. In that case, I can say that it is irregular singular point of given differential equation. Then I should come to know that I am unable to find out the solution of the given differential equation. It means I am unable to find out series solution of the given differential equation of this form, right. Of this form means y is equal to x to the power m a naught plus a1 x a2 x square and so on, or you can write down summation of ak x to the power m plus k, k varies from 0 to infinity, right. So, when x is equal to 0 is an ordinary point of the given differential equation. Okay. So, now I want to find out the series solution of this equation, right. So, I will assume that x is equal to 0 is an ordinary point. Then I can assume, according to the condition, I can assume the solution of this differential equation is y is equal to a naught plus a1 x a2 x square and so on, or you can write down using the summation ak x to the power k, k varies from 0 to infinity, right. So, now I want to differentiate this equation. Is it clear? So, y is equal to, so therefore, dy by dx is equal to, observe the first term. What is the first term? First term is a naught. A naught means it is a constant. So, differentiation of constant is 0. Now, I want to differentiate second term with respect to x. So, a1 is a constant, x with respect to x is 1, right. And similarly, a2 derivative of x square is 2x. So, it means it can be written as 2 times of a2 into x. Similarly, a3 x to the power 3 can be differentiated. So, a3 I will keep as it is, derivative of x cube is 3 times of x square. So, like that, right. Or you can differentiate summation of ak x to the power k. So, what I have written here. So, dy by dx can be written as, you observe in this summation I have written k is equal to 0 to infinity. In this summation k varies from not 0 to infinity, 1 to infinity into, sorry, summation of k into ak x to the power k minus 1. So, why I have written k is equal to 1? Because just now I have explained. So, here first term is the constant. When we differentiate all these terms, first term becomes 0. So, that is why we want to write instead of 0, you can write down k is equal to 1 to infinity. All other terms remains or exist except first term when we are differentiating all these terms. So, that is why I have replaced k by 1 to infinity. Okay. So, now I want to differentiate one more time. As I have mentioned, when we differentiate this equation one time, first term becomes 0 and second term becomes constant. Why? Because second term containing only x. When I differentiate first time, x with respect to x and a1 becomes a constant, right? So, that is why when we differentiate this equation two times, second term becomes 0, first term as well as second term becomes 0, right? And third term I can differentiate as usual. You know the formula, is it clear? So, that is why I have written d square y upon dx square is equal to k varies from 2 to infinity. I have not written 1, right? So, we must write k is equal to 2 to infinity. So, k into ak x to the power k minus 1. So, using the formula x raised to n, it can be differentiated. So, n into x raised to n minus 1, right? So, that is why I have written k into k minus 1 ak x to the power k minus 2, right? So, you know the value of y and you know the value of dy by dx and we know the value of d square y upon dx square. So, now you want to substitute these values in the given equation. So, what is the given equation? Given equation containing d square y upon dx square, dy by dx and y, right? So, I will substitute all these values in equation 1 and you can replace k by 1, 2, 3 and so on. You will get various terms, right? So, then I want to find out the coefficients of various powers of x. So, why? Because I want to equate to 0 the coefficients of various powers of x and I want to find out the values of a2, a3, a4 and so on in terms of a0 and a1. It means our series solution must contain a0 and a1 or our series solution can be expressed in terms of a0 and a1 only. That is why we want to find out the values of all these constants and you can substitute these values in the assumed solution, right? Equate to 0 the coefficient of x to the power n. As I have mentioned, I want to obtain various powers of x. Various powers of x means x to the power 0. What is the coefficient of x to the power 0? What is the coefficient of x to the power 1? What is the coefficient of x to the power 2, x to the power 3? In general, I want to find out what is the coefficient of x to the power n. It is important. Why? I want to call the coefficient of x to the power n as an recurrence relation, right? So, why I want to calculate or I want to write down a recurrence relation? Because as I have mentioned, now I want to calculate a2, a3, a4, right, a5, a6 and so on. I cannot calculate individually. Individually means, say for example, now I want to calculate a10, a20th term. It is not possible to calculate. It means the entire process becomes tedious, right? To avoid that one, you can write down the recurrence relation. So, once we are able to write down a recurrence relation, in that recurrence relation or from the recurrence relation, suppose if I want to calculate a 20th term, I can obtain very easily simply by replacing n by some number. That is why recurrence relation plays an important role, right? So, as I have mentioned here, give different values to n in the recurrence relation to determine various ai's in terms of a0 and a1. Okay, you assume that, so we will calculate the value of a2, a3, a4 and so on, right? So, you can substitute these values in the equation 2. So, equation 2 means assumed solution. To get this series solution of 1 having a0 and a1 as arbitrary constant, and that becomes the solution of the given differential equation. Okay friends, I have explained theory part how we want to find out series solution, right? So before considering the Bessel's equation, now I want to consider a very simple example. How do we find out the series solution of this equation, right? So observe, it is given that d square y upon dx square and its coefficient is 1 plus x into y is equal to 0, and right. So now I want to verify whether I can able to obtain a series solution of this equation or not. So clearly I can say that, so I am able to find out the series solution of this equation. How do we say that I will get the series solution for the given differential equation? So I want to verify the condition. Put x is equal to 0 in the coefficient of d square y upon dx square. So what is the coefficient of d square x upon dx square? 1. It means is equal to 0. It means polynomial is not equal to 0. X is equal to 0 is an ordinary point of the given equation, right? So according to the condition, I can assume the solution of this differential equation is y is equal to a naught plus a1x plus a2x square plus a3x to the power 3 and so on. Or I can write down summation of k is equal to 0 to infinity ak into x to the power k, right? Okay. Now I will differentiate this equation. So dy by dx is equal to, so first term is constant and it becomes 0. Second term is not constant. I will keep a1 as it is. X with respect to x is 1. That's why I have written a1 only. Plus a2 into x square. Derivative of x square is 2x. That's why I have written 2 times of a2 into x. Plus next term. Derivative of next term. What is the next term? a3 into x to the power 3. 3 times of a3 into x square and so on. So finally, nth term can be written as n into an x to the power n minus 1 plus so on, because it is containing infinitely many terms. Okay, we have obtained dy by dx. Exactly in the similar way, now I want to differentiate one more time d square y upon dx square, that is equal to. So again, in this case, first term is constant, a1 is constant. So if I differentiate a1, I will get equal to 0, right? Plus 2 is constant, keep as it is. a2 is constant, keep as it is. So derivative of x with respect to x is 1. That's why I have written it as 2 into 1 into a2 plus 3 constant, keep as it is. Derivative of x square is 2x, a3 is constant. Similarly, plus 4 into 3 into a4 x to the power 2 and so on. Nth term is n into n minus 1 an x to the power n minus 2. So it means, so you have to practice all these things. So it means you want to differentiate term by term. Better you can write few more terms, differentiate, right? So when we are able to obtain all these things, we want to substitute these things in the given differential equation. Okay. So now I know the value of d square y upon dx square, right? So this is the right hand side. I will substitute all these terms in this equation plus x into, what is the value of y? Y is assumed solution. I am going to replace y by all these terms, right? Now I want to rearrange the terms. Okay, so this is the given equation. Substitute in the given differential equation y and d square y upon dx square. So I will replace d square y upon dx square by its value. This is the value of d square y upon dx square. I have written 2 into 1 into a2 plus 3 into 2 into, it is multiplication, it is not 32, 3 into 2 into a3 into x plus 4 into 3 into a4 into x to the power 2 and so on. So plus n into n minus 1 an x to the power n minus 2 and so on, right? I have replaced the value of d square y upon dx square plus x into, that's why what I have written here, plus x into y. So what is the value of y? What I have written here, a naught plus a1x plus a2x square plus a3 into x to the power 3 plus so on an into x to the power n is equal to 0. Simply I have differentiated the assumed solution 2 times, then I have replaced in the given equation and I have obtained this equation, right? So now I want to rearrange the terms. Is it clear? As I have mentioned in the theory, now I want to obtain various powers of x. It means I want to find out what is the coefficient of x to the power 0, what is the coefficient of x to the power 1. In that direction, I want to rearrange all these terms. Okay. Now you observe the first term 2 into 1 into a2. Similarly, you observe whether coefficient of a2 is present in this equation or not, along with the x to the power 0. So this series does not contain x to the power 0 coefficient. That's why, so it is containing only one term. That's why I have written the coefficient of x to the power 0. Right. So x to the power 0 means it is 1. 1 can be written as x to the power 0. What is the coefficient of x to the power 0? 2 into 1 into a2. Right. So now from these two series, now I want to collect the terms coefficients of x to the power 1. Okay. So you observe second term. So x, its power is 1 and its coefficient is 3 into 2 into a3. So what I have written here. Right. And similarly, now I want to collect what is the coefficient of x to the power 1. Is it clear? So first term a0, because x is outside, I want to multiply x into all these terms. So that's why I can say that in this part, the coefficient of x to the power 1 is a0. What I have written here, 3 into 2 into a3 plus a0, right, into x. Okay. Exactly in the similar way, now I want to collect what are the coefficients of x to the power 2, 4 into 3 into a4, right. And similarly, here also I want to identify what are the coefficients of x square. a1x into x means a1x square. So it means the coefficient of x square is a1, what I have written here, 4 into 3 into a4 plus a1 into x square. Similarly, now I want to identify what are the coefficients of x to the power 3. So I will get 5 into 4 into a5 plus a2 into x to the power 3 and so on. Similarly, you can write down x to the power 4 its coefficient, x to the power 5 its coefficients and so on. In general, I can write down what are the coefficients of x to the power n. I can obtain on the basis of all these terms, I am able to write down n plus 2 into n plus 1 a n plus 2 plus a n minus 1 into x to the power n plus so on is equal to 0. Right. So now we can write down one by one. What are the coefficients of x to the power 0? So it means I hope we will get a2 is equal to 0. So when you observe the first term, 2 into a1 is equal to 0, because I want to equate the coefficients of here is powers of x. First term is x to the power 0. The coefficient of x to the power 0 is this, right, is equal to 0. So therefore a2 is equal to 0. So like that you can obtain the value of a2, right. And similarly, what are the coefficients of x to the power 1? I hope you will get these two terms, right. So when we observe the previous equation, right, it is containing two terms, 3 into 2 into a3 plus a0 is equal to 0, right. I hope so you will get from this you can obtain the value of a3. 3 into 2 into a3 is equal to minus times of a0 divided by 3 into 2 is 6. 6 can be written as 3 factorial. Like that you can obtain the value of a3, right. And similarly, from the next term you will get 4 into 3 into a4 plus a1 is equal to 0. So how do we get it is coefficient of next to the next power, x to the power 2, right. 4 into 3 into a1 plus a1 is equal to 0. Similarly, what is the coefficient of x to the power 3? I will equate it to 0. So you will get a5 is equal to a4 is equal to, like that we can obtain, right. So from this term you can obtain a4 is equal to, you can take a1 to right hand side. So that's why I have written minus times of a1 divided by, so it is 4 into 3. 4 into 3 means 12, right. So now I want to write in terms of factorial in a particular pattern. That's why I have written 4 factorial, but it is 12. To adjust the term, that's why I have multiplied numerator by 2. I hope you will get the value of a power. And similarly, 5 into 4 into a5 plus a2 is equal to 0. So therefore a5 is equal to minus times of a2 divided by, so 5 into 4 and so on, right. So in general, from the nth term, what is the coefficient of x to the power n? N plus 2 into n plus 1, a n plus 2 plus a n minus 1, right. So therefore a n plus 2 is equal to, I will take this term to right hand side. So minus times of a suffix n minus 1 whole divided by n plus 2 into n plus 1. So this we call it as a recurrence relation. Is it clear? So far we have calculated A5. Suppose now if I want to calculate A6, how do we calculate A6? It is very simple, right. So a suffix n plus 2, I am going to replace n by 4. You will get a suffix 6 is equal to, right hand side also I have to replace n by 4. A suffix 4 minus 1 means a3 divided by 4 plus 2 is 6, 4 plus 1 into 5. It means I can write down 6 into 5, right. Not necessarily a6. Suppose if you want to calculate a6, a7, a10 and so on, all those terms can be calculated from the recurrence relation. So that is why a recurrence relation is an important, right. So we call it as a recurrence relation. Simply you want to replace n by 4, 5, 6 and so on. I hope you will get a6 is equal to a3 by 6 into 5. It is multiplication, not 65, right. So that is equal to, as I have mentioned, now I want to obtain our solution in terms of a0 and a1 only, right. Our solution must contain only two arbitrary constants, namely a0 and a1. That is why already I have calculated the value of a3, right. I will substitute the value of a3 in this equation. Simplify, I hope you will get 4a0 by 6 factorial. Okay. Now I will calculate a7. How do you calculate a7? From the recurrence relation. Now I want to replace n by 5. 5 plus 2, 7. 5 minus 1, a6 divided by 5 plus 2, 7. 5 plus 1, 6. I hope you will get this term, right. So again a4 is known. I have already calculated a4. I will substitute the value of a4 in this, then I can simplify, I can obtain. So 5 into 6, sorry 5 into 2 into a1 divided by 7 factorial and so on. Suppose if you want to calculate a8, it is possible to calculate. And now I want to substitute all these constants in the assumed solution. I can obtain y is equal to a0, because our terms a6, a7, a8 or a3, a2, all those terms containing either in terms of a0 or in terms of a1, right. Now I will collect all the coefficients of a0. I will write down in this form. So that is why you will get y is equal to a0 into 1 minus x to the power 3 divided by 3 factorial plus 1 into 4 into x to the power 6 divided by 6 factorial minus 1 into 4 into 7 x to the power 9 divided by 9 factorial and so on, right. Plus what are the coefficients of a1? I will collect and I will write down in this form. a1 into x minus 2 x to the power 4 divided by 4 factorial plus 2 into 5 into x raised to 7 by 7 factorial and so on. And this becomes the solution of the given differential equation. Okay. Now I want to modify the previous example, right. So it was given that d square y upon dx square plus x into y is equal to 0. Here instead of x, what I have written? X square. Is it clear? Right. So now I want to find out the solution of this differential equation. So procedure remains the same. First I want to verify whether I am able to calculate series solution or not. I have to verify whether x is equal to 0 is an ordinary point or not. So clearly the d square y upon dx square is 1, it is not equal to 0. So therefore x is equal to 0 is an ordinary point of the given differential equation. Then you can assume the solution of this differential equation is y is equal to a0 plus a1x plus a2x square and so on, or you can write down in terms of summation ak x to the power k, k varies from 0 to infinity, and you may call it as an equation number 2. Like previous example, you can differentiate all these terms, and we know that a0 is constant. When we differentiate a constant term, I can obtain 0. So I will get a1 derivative of x with respect to x is 1, derivative of second term is 2x, 2a2x plus 3a3x square and so on, right. So, nth derivative is n into an x to the power n minus 1, or in terms of summation, right. So, a k is constant, x to the power k is k into x to the power k minus 1, where k varies from 1 to infinity, right. So, again first term is constant. When we differentiate one more time, again it becomes 0. So, when we differentiate second term, it is containing x with respect to x is 1. That is why you will get 2 times of a2, x with respect to x is 1. That is why I have written 2 into 1 into a2. Similarly, derivative of x square is 2x. So, 3a3 is constant. That is why 3 into 2 into a3 into x, right, and so on. What is the nth term? N into n minus 1 a n x raised to n minus 2 plus so on, or in terms of summation you can write down k into k minus 1 a k x to the power k minus 2. Again, by using the formula x to the power n, it can be differentiated. X to the power n means n into x raised to n minus 1, x to the power k minus 1 means k minus 1 into x to the power k minus 2, right. So, I have obtained the value of dy by dx, the value of d square y upon dx square, and I have assumed y. So, now I will substitute all these values in the given equation. What is the given equation? So, d square y upon dx square plus x square y is equal to 0 is the given equation. Is it clear? Right. So, now I will substitute in terms of summation. In the earlier example, I have replaced direct values, right. So, now I will replace in terms of summation. The value of d square y upon dx square is equal to k into k minus 1 a k x to the power k minus 2, k varies from 2 to infinity, plus the coefficient of y is x square, right. The value of y is the summation of a k x to the power k, k varies from 0 to infinity. Is it clear? So, now I want to replace k by 2, k by 3, k by 4 and so on. I want to write down, or I want to expand this summation. Similarly, I want to expand this summation. Now, I want to collect, like previous example, various powers of x. What is the coefficient of x to the power 0? What is the coefficient of x to the power 1? What is the coefficient of x to the power 2 and so on, right. Then you can equate it to 0, and finally you want to find out the recurrence relation, right. So, when we replace k by 2, I hope you will get the coefficient of x to the power 0 is 2 into 1 into a2 plus 3 into a2 into 3 into 2 into a3x plus 4 into 3 into a4 x to the power 4, so on, plus n minus 2 into n plus 1 a n plus 2 x to the power n and so on, plus x square. In this case, I can replace k by 0. I hope you will get x square into a naught plus a1x, a2x square and so on. Is it clear? Equal to 0, right. So, coefficient of x to the power 0 is 2 into 1 into a2, right, plus coefficient of x is 3 into 2 into a3. Coefficient of x square, you will get 2 terms, 4 into 3 into a4 plus a naught. Similarly, coefficient of x to the power 3, again you will get 2 terms, 5 into 4 into a4 plus a1. And in general, what are the coefficients of x to the power n? I hope you can obtain, like a previous example, n plus 2 into n plus 1 a suffix n plus 2 plus n minus 2 into x to the power 1 is equal to 0. So, from this we can obtain the recurrence relation, right. So, when we equate x to the power 0, so I hope you will get a2 is equal to 0 and a3 is equal to 0. So, in general, so from this you can obtain a recurrence relation, right. A suffix n plus 2 is equal to 0. I will take this term to right hand side, that is why I will get minus times of a n minus 2 whole divided by n plus 2 into n plus 1, right. So, in this series, if I replace n by 2, 3, 4, 5 and so on successively, I can obtain, when we replace n by 2, a suffix 2 plus 2 means 4, that is equal to a naught. 2 minus 2 means you will get a naught divided by 2 plus 2 means it is 4, 2 plus 1 is 3, 4 into 3. So, like that I can obtain a4 and a5 so on. Okay. Now, when we replace n by 2, I can obtain a4 is equal to a naught by 3 into 4 from the recurrence relation. Again, it is in terms of a naught only, or the same thing can be written in this form. When we replace n by 3, 3 plus 2 is 5, 3 minus 2 is 1. I hope you will get in terms of 1 minus a1 divided by 4 into 5. That's clear. Similarly, you can obtain a6, replace n by 4, 4 plus 2 is a6, right. So 4 minus 2 is 2, right. So 4 plus 2 is 6. So 4 plus 1, 5, 5 into 6. But a2 can be written in terms of a1. Is it clear? So similarly, you can obtain a7 is equal to a3, 6 into 7. I hope you will get all these values as a 0, right. So a8 can be obtained. Similarly, by replacing n by 6, when we replace n by 6, I hope you can obtain a6 again in terms of a0. I hope you will get a0 by 3 into 4 into 7 into 8. Okay. Now I can obtain a9. a9 means I have to replace n by 7. You will get a5. So again a5 is known. You want to substitute and we have to simplify. After simplification, I can obtain a1 by 4 into 5 into 8 into 9 and so on, right. So now I want to substitute all these constants in the assumed solution in equation 2, and then I can collect the coefficients of a0. You can write down y is equal to a0 into 1 minus x to the power 4, 3 into 4 plus x to the power 8 whole divided by 3 into 4 into 7 into 8 and so on. Similarly, I can collect the coefficients of a1. Then I can write down in this form x minus x to the power 5 divided by 4 into 5 plus x to the power 9 whole divided by 4 into 5 into 8 into 9 plus so on, and this becomes the solution of the given differential equation. Okay. So now I want to improve my previous example. Actually, it was containing only two terms. First example was d square y upon dx square plus x into y is equal to 0. Then I made it as an d square y upon dx square plus x square into y is equal to 0. Still I want to make it as an complicated one. Complicated one means I want to add one more term. Is it clear? So I think it is containing only two terms. Now it is containing 1, 2, 3 terms. And the previous example was containing d square y upon dx square plus x into y. Here I have included one more term, namely dy by dx. Right. In the previous example, the coefficient of d square y upon dx square was 1. Here I have included the coefficient of d square y upon dx square is other than 1. Other than 1 means it is given that 1 plus x square into d square y upon dx square plus x into dy by dx minus y is equal to 0. Is it clear? You should not upgrade of this equation because the procedure is same. Is it clear? Procedure of finding the solution of this differential equation is same. Same means first I have to verify x is equal to 0 is an ordinary point or not. How do we verify? So here p naught x is equal to 1 plus x square. So in this case I want to replace x by 0, 1 plus 0, and it is not equal to 0. When x is equal to polynomial is not equal to 0, when x is equal to 0, it means so x is equal to 0 is an ordinary point. Therefore, I can assume the solution. How I have assumed in case of previous example. Exactly in the similar way, you can assume the solution of this differential equation as a series solution. Again, you have to find out dy by dx, d square y upon dx square. Then you want to substitute the value of d square y upon dx square, the value of dy by dx, the value of y, right? And you want to rearrange all the terms. It means you want to collect what are the coefficients of x to the power 0, what are the coefficients of x to the power 1, x to the power 2, in general x to the power n, right? Then you will get the recurrence relation. Again you can find out some more values and you can express in terms of a0 and a1. Then you can substitute all those values in this equation. That is the solution. Okay. Now here x is equal to 0 is an ordinary point. Right. So now I can assume the solution of this differential equation is a0 plus a1x, a2x square and so on, or you can write down in terms of summation. Is it clear? Then you can differentiate, as I have mentioned, a0 is constant, it becomes 0. So derivative of second term a1, x with respect to x is 1. Derivative of next term 2 into a2 is constant, derivative of x square is 2x, that's why I have written 2x. Similarly, derivative of third term and so on. Derivative of nth term, n into a n into x to the power n minus 1, that is equal to, you can write down in terms of summation. While writing in terms of summation, you must take a care, right, while writing dy by dx. So here I have written k is equal to 0 to infinity. I want to write k is equal to 1 to infinity, because here first term is not equal to 0. In dy by dx, first term becomes 0. Is it clear? And similarly, again dy by dx containing a constant term. When we differentiate a constant term, it becomes 0. That's why now I will differentiate the next term. 2 is constant, a2 is constant, x with respect to x is 1. That's why I have written 2 into 1 into a2 and so on. You can find out the nth derivative. So n is constant, an is constant, right? So x to the power n minus 2. Or you can write it in terms of a summation. Here k varies from 2 to infinity in the second derivative. So k is constant, ak is constant, x to the power k minus 1 means k minus 1 into x to the power k minus 2, right? So I have obtained the first derivative as well as second derivative of the assumed solution, right? So now I will substitute all these values in equation number 1. So 1 minus x square into, is it clear? 1 minus x square into the value of d square y upon dx square, k varies from 2 to infinity, k into k minus 1 ak x to the power k minus 2 plus x into the value of dy by dx, k varies from 1 to infinity, ak x raised to k, right? So minus ak x raised to k. So I think the value of dy by dx is k into ak into x to the power k minus 1, right? So here I have to write, so k into ak into x to the power k, right? So this is the value of y, k is equal to 0 to infinity, ak x to the power k is equal to 0. Okay, so now I have substituted all the values. All the values means the value of d square y upon dx square, the value of dy by dx, the value of y. So now I will multiply 1 plus x square into, it is actually 1 plus x square into as it is, right? You can expand, replace k by 2, k by 3 and so on. You will get all these terms like previous example, right? Plus x into, in this summation you want to replace k by 1, 2, 3 and so on. You will get all these terms, minus summation of k is equal to 0 to infinity, replace k by 0, 1, 2, 3 and so on. You will get all these terms equal to 0. So now I want to identify various powers of x. You can rearrange the terms. Is it clear? I hope various powers of x we can obtain. a2 is equal to a0 by 2 and a suffix 3 is equal to 0, equating to 0 the coefficient of x to the power n, as I have mentioned in the previous examples, right? You can obtain the recurrence relation. What is the recurrence relation? You will get a suffix n plus 2 is equal to minus times of n minus 1 divided by n plus 2 into an, right? So here from this recurrence relation you can obtain the various values. When we replace n by 2, I hope you will get a4. When you replace n by 3, you will get a5. Is it clear? And a6, right? You can find out all these values. Is it clear? And we want to simplify these values in terms of a0 and a1 only. Is it clear? Now I will substitute all these values in the assumed solution. I hope you will get a0 into 1 plus x square by 2 minus x to the power 4 by 8 plus x to the power 6 divided by 16 minus times of 5x square divided by 128 and so on. So this becomes the required equation of the solution. Is it clear? So exactly in the similar way, now the given equation may be in this form. Now x is equal to 0 may not be a regular point. Is it clear? When x is equal to 0 is a regular singular point of the given equation. Is it clear? So in that case, as I have mentioned earlier, you want to assume solution in this form. Solution in this form means, say for example, y is equal to x to the power m a0 plus a1x plus a2x square plus a3 into x to the power 3 plus so on. Nth term means an x raised to n plus 1, or you can write down in terms of summation. Is it clear? Right? So now you want to differentiate this equation, first derivative, second derivative, then you want to substitute in this equation, right? Then you can rearrange the terms. Is it clear? Right? So we shall discuss all these things in the next session. So thank you.